Okay, in this video we're going to look at problem number 1 on the worksheet. And part A says, show that the line described by the vector function r of t that has components negative 2 plus 3t, comma 5t, comma 1 minus t has 0 curvature. Okay, now up above I've included our main results from the last video. All right, we define the curvature to be the magnitude of the derivative of the unit tangent vector with respect to arc length. And then using the chain rule, we derive the second expression for curvature, and this is equal to the magnitude of the derivative of the unit tangent vector with respect to time divided by the magnitude of the velocity vector. Okay, now a way to describe curvature is to say the following, right? At what rate will our direction have to change in order to stay on our path? Well, if I'm moving along a straight line path, our direction, in fact, doesn't change at all. So for that reason, it makes perfectly good sense that this line would have 0 curvature. Well, let's actually carry out the calculations. So our velocity vector, that's found by just differentiating the position vector component-wise. So that's 3, 5, negative 1, and we note here that that's a constant vector that points parallel to our line. And we also have constant speed, right? That turns out to be the square root of 35. All right, now the unit tangent vector, that's found by dividing the velocity vector by its magnitude. So that gives us this vector here, which we know is also a constant vector. And up here you see that the unit tangent vector is the unit vector that points in the direction of our velocity vector. All right, now since the unit tangent vector is itself a constant vector, its derivative with respect to time is the 0 vector. So that implies, using the second expression for curvature up above, that the curvature of this line is 0 for all t. Okay, and more generally, any line, either in R2 or in R3, has 0 curvature, really by the same argument. All right, great. So now let's turn to part B. This says to show that the circle described by the vector function r of t, which is equal to capital R cosine t I plus capital R sine t j, where here capital R is a positive constant, has constant curvature. Okay, so here the I and the j components give us a counterclockwise parameterization of the circle of radius r centered at the origin. Here I've just indicated a few unit tangent vectors along our path. And to say that this circle has constant curvature is to say that this unit tangent vector has to change its direction at a constant rate in order for us to stay on our path. And that makes perfectly good sense, just given the shape of the circle, right? No matter where we are on the path, right, the amount that I'm going to have to turn to stay on the path will be the same regardless of where I am actually on the path. All right, so we're going to have constant curvature. Now the question is, what is that constant curvature, right? How does it relate to the radius of the circle? Well, let's do the calculations. So the velocity vector, again, we can find by just computing the derivatives of the component functions of our position vectors. That's negative r sine t I plus r cosine t j. And then the magnitude of the velocity vector, right, our speed, is constant. It's r, and that follows just from the Pythagorean identity. And so our unit tangent vector, capital T, that is found by just dividing the velocity vector by its magnitude. And so dividing v, right, by the radius of the circle r, you notice those r's cancel out, and that leaves us with negative sine ti plus cosine t j. All right, so now I want the derivative of the unit tangent vector with respect to time. So I'm going to differentiate this green vector with respect to time. So that gives us negative cosine ti minus sine tj. And I note here that it has magnitude 1 from the Pythagorean identity. All right, so then I can measure the curvature as follows. Okay, so this is the ratio, right, of this magnitude of the derivative of the unit tangent vector with respect to time, and we found that to be 1. And I'm taking the ratio of that with the magnitude of the velocity vector, which we found up here is constant, right? It's just the radius of the circle. So in conclusion, we have that a circle of radius r has constant curvature, and that is equal to 1 over the radius of that circle, 1 over r. Okay, so as a consequence of this, right, the larger the radius, the smaller the curvature. Okay, an explanation for that is as follows, right? So let's say we're on this circle with smaller radius. Well, in order to stay on this path, our direction is going to have to change at a faster rate than it would for this circle that has the larger radius, right? Here with the larger radius, we just don't have to change our direction as much to stay on this path. So there's this inverse relationship between radius and curvature. All right, great. Well, that's a good place to stop. I'll see you in the next video. Thanks so much.